Welcome to this course on advanced reaction engineering. I will take you through the different things that we are going to learn in this course. But this first lecture, I would like to devote to revising little bit about our undergraduate chemical reaction engineering course and some of the things that we have learned in our undergraduate chemical reaction engineering course, because that's going to form the basis for this course. So let's just get started with our course. Let's just start with this first lecture. I would like you to recall all the basic concepts that you have learned in your undergraduate course. That's the first thing that I would like you to do. As a starting point, I would like you to write in your notebooks examples of reactors that you have come across. So this is a pre-recorded lecture. So therefore, in the lecture, I will tell you at different places to pause the video and do some exercise for yourself, or solve the problem, or derive something for yourselves. So it's a good idea that you follow these instructions. So right now, stop the video and answer the question in your notebook. You can make a notebook and you can write down your names of examples of reactors that you have come across in your undergraduate course, not just in reaction engineering, but in any other course as well. Maybe in industrial engineering chemistry, you have learned about different types of reactors, say for example, ammonia reactor or sulfuric acid contact process, or maybe paraxylene oxidation to terephthalic acid. Different kinds of reactors that you have thought or you have seen or you have heard of in your undergraduate course throughout the 4 years. So pause the video and write down for yourself a list. Here is something that you might have written. You might have written batch reactor, you might have written plug flow reactor, you might have written CSTR, you might have written slurry reactor, you might have written packed bed reactor, you might have written trickle bed reactor, fixed bed reactor, fluidized bed reactor, hydrogenation reactor, oxidation reactor, chlorination reactor, and so on. You might have written so many things. Okay? You have come across all of these, or at least some of these, and these names are quite a diverse list. For example, if you say hydrogenation reactor, that means it involves reduction using hydrogen of some compounds. If you have written oxidation, it involves oxidation using maybe oxygen, using ozone, using sodium hypochlorite, or some other oxidation medium, or some other oxidation oxidant. Chlorination, it could be say photochlorination you have heard of, or you have written fluidized bed reactor or trickle bed reactor. You might have written for example, say hydrodesulfurization or something like that. Now just pause and just write down as many reactors that you have come across. Okay, what I would like you to do further is the following. First, can you think about some characteristics of each of these reactors? Some characteristics. So for example, batch reactor, if you are saying characteristic would be, okay, it's a vessel in which there is an agitator, we charge things, we do the reaction, we heat up, we do the reaction, we cool down, we remove the product, and so on and so forth. Packed bed reactor, you might have written something, you can write whatever that comes to your mind about each of these. Just write down in front of that particular reactor some characteristics. It may not be complete, it may or may not be accurate, but let's not worry about that just now. Just write down some characteristics that you have come across, or you remember about these reactors. Next point I would like you to think about is, can you classify them? Classify means, can you segregate based on the characteristics that you have written? Can you segregate them into different categories? I would like you to segregate them into different categories. So when I say segregate, or when I say classify, means club different reactors which have similar characteristics, club them together, put them under one column, if you like. And some other characteristic you might be aware of, and you want to club different reactors that you have written examples of, club them together, put it in a separate column if you like. So like this, I would like you to classify all of these reactors into different groups. Pause the video, do this for yourself. Here are some of the characteristics that we can think of. Maybe you have thought of some of these characteristics, maybe you have thought of all of these characteristics. It is good. One category could be depending on what phases are involved. So if it's a homogeneous or a single phase reaction, or it is a heterogeneous reaction involving multiple phases. So when we say multiple phases or heterogeneous, what we mean, there is a gas and a liquid, or a liquid and a solid, or a gas and a solid, or a liquid and liquid, aqueous and organic. So this is what we mean by heterogeneous. Under heterogeneous, you can think about different categories, right? You can think about how these phases come together, how gas and liquid come together. Is there a dispersion created? Means one phase is dispersed in the form of bubbles or droplets into another, or is there a flow of film of one over the other phase? You could classify them based on flow behavior, whether the two phases that you have thought of or that you are thinking of, whether they flow co-currently, whether they flow cross-currently, whether they flow counter-currently. Remember, co-current, cross-current, counter-current, you have come across these things when you are doing extraction, when you are doing unit operations, distillation, absorption, and so on and so forth. So these are all applicable here as well. It is how these two phases flow against one another. Third thing that you could have thought of is how the energy is supplied for generating this dispersion or making this flow possible. You could have thought of, say, maybe mechanical agitation. Maybe there is an agitator which is receiving power from a motor. That's a mechanical agitation. So that mechanical agitation is what is creating dispersion of one into the other. That is what is making the phases flow. There could be pressure or buoyancy force. We will talk about these as we go along. For example, when we say pressure, you could have a liquid inside a reactor, and you can bubble gas through that reactor like a bubble column. Okay? So then gas flows in the form of dispersion by way of the pressure of the gas, or buoyancy of the bubbles take these bubbles upward. Okay? So that's what we mean by a buoyancy force, or that's what we mean by pressure force. Other thing that you can think of is perhaps potential energy. Maybe there is a spray of liquid. So you are taking a liquid to at a height and spraying it through a nozzle, or you are allowing the liquid to flow down in a packed column. So you have applied potential energy, you have made the liquid go up. It has now a higher potential energy, and it is flowing because of gravity through a column. So your absorber, you might have heard or you might have seen in your undergraduate course, that's an example of potential energy. So different reactors you can classify based on these different characteristics. Some other characteristics you might have thought about is whether the reactor is operated as a batch wise, whether the reactor is operated in a semi-batch manner, or whether it is a continuous manner. Another thing that you could have classified it as dynamic behavior, meaning whether the reactor is being operated under steady state conditions or whether it is being operated under unsteady state conditions. That means where concentrations, temperature, pressure is changing with respect to time. That's what we mean by unsteady state. You could have classified these reactors in terms of mixing behavior. Plug flow reactor, non-ideal flow, you might have heard, or well mixed reactor, right? Or you could have classified them based on heat effects, whether there are any heat effects, whether the reactor is operated as adiabatic, means no heat transfer is exchanged with the surroundings, no heat is removed or no heat is added, or it could be a diabatic where heat transfer is allowed. And one extreme example of diabatic is when the reactor is operated under isothermal conditions. So when you think about all these different things, try to classify all of these using these classification using these characteristics. Let me give you an example. So for example, if you have thought of, let's say, hydrogenation reactor, where you are, let's say, hydrogenating nitrobenzene. Okay, so hydrogenation of nitrobenzene you could have carried out in a batch manner, you can carry out in a semi-batch manner, or you can carry it out in a continuous manner. You can carry it out in a batch reactor, then it will be steady state. Sorry, if you are carrying it out in a batch reactor, it would be unsteady state. If you are using it in a continuous manner, it could be a steady state. You could have a plug flow of nitrobenzene and hydrogen. They could be co-current, counter-current. You could have a well-mixed behavior for nitrobenzene and hydrogen. Again, these are independent of one another. These characteristics are independent of one another. We can have any one of these characteristics, any one of these characteristics, any one of these characteristics, any one of these characteristics. Nitrobenzene reduction to aniline, we can operate in an adiabatic manner. We could operate in an isothermal manner. Say ammonia reactor, for example. Ammonia reactor, where we make nitrogen and hydrogen flow over a packing, which is a catalyst for the reaction, say ion catalyst. So there it's a heterogeneous reaction. Nitrogen in the gas phase, hydrogen in the gas phase is reacting on the surface of a catalyst particle. So gas solid kind of reaction. There's no question of co-current, counter-current, cross-current, because the solid is stationary. It's only the gases that are flowing. But they are flowing because of pressure energy. We are supplied nitrogen, hydrogen under pressure, and that is making them go across the reactor. We don't have a dispersion or a film flow. It is actually the solid particles are in a packed form and the gas is flowing around. So you can think of it as a dispersion, if you like. Dispersion is so concentrated that it becomes a packed bed. Ammonia reaction is made in a continuous manner. It is not made in a batch manner. So nitrogen, hydrogen are operating, coming in, reactors operating continuously. Nitrogen, hydrogen are coming in, ammonia is going out continuously. And it's a steady state operation. The reactor is also plug flow. Nitrogen and hydrogen flow in a plug flow manner across the solid particles. Catalyst. It is not well mixed. It is operated under adiabatic mode, right, where temperature is allowed to increase because of exothermicity of the reaction. It is not isothermal. So you see, all these characteristics are independent of each other. Now think about any reaction. Stop the video, go to your industrial engineering chemistry course. Think about all the things that you have learned there, all the processes that you have learned there. Look at the reactor in each of these processes and look at that reactor under each of these, look at these reactors and try to identify each of the characteristics that we have described just now. Each reactor you should be able to classify based on, or for each of these reactors you should be able to describe all these 5 kinds of things. Okay, go ahead, stop the video. Stop the video, do this exercise yourself. It may appear trivial to you, it may appear boring, you are trying to recollect something from your second year, third year, but it is worth the exercise. Think about all the reactors that you studied in your all the processes, industrial engineering chemistry, and classify each of these processes, each of these reactors in each of these processes. Describe them by these 5 categories that we have seen, because this is the most important thing to do in the course. Okay? Whole course is going to be based on this classification. I will tell you as we go along. Whole course is geared around, or whole course is centered around these things. Couple of points I would like to emphasize. One is any reactor can be described by the above characteristics. That's the exercise that I have given to you. And if you have to characterize, or if you have to design, or if you have to tell about a reactor, you need to specify all these 5 things. If any one of these 5 things you have not described, or you have not characterized the reactor by, your description is incomplete. Okay. What we are going to do in this course is centered around all these things. First of all, what we are going to very briefly look at plug flow, non-ideal, well-mixed kind of behavior. Okay. We will mainly discuss them under isothermal conditions. We will talk about them from a batch point of view, from a continuous point of view. So flow behavior, dynamic behavior, mixing behavior. These are the things that we are going to do in the first part of the course. Okay. Later on, second part of the course, we are going to look at multi-phase reactions, where we are going to look at gas solid or a fluid solid kind of reactions, as well as fluid fluid reactions, right? And next semester there will be a course on multi-phase reactions or multi-phase reactor engineering, or multi-phase reactors in general, which will be an extension of what we are going to do in our advanced CRE course. Okay, so this classification is the underlying theme for our course. I would like to start this course by revising a few concepts from our undergraduate reaction engineering course. Take out your notes for undergraduate reaction engineering. Take out all the all the textbooks that you have used for your undergraduate chemical reaction engineering course. Try to recall all those concepts. Pause the video, do a revision for yourself. Okay, some concepts I am going to tell you in the in this lecture. Okay, pause the video, study for yourself, revise for yourself. Again and again I am emphasizing, unless you pause and unless you study, you will not derive maximum benefit out of these lectures. These lectures are pre-recorded. Okay, so you have to stop them at appropriate point and do whatever is asked of you to do. Only then the course is complete. Your course is of 45 hours duration. Recorded lectures are not going to be of 45 hours. They may be about 20 hours or 25 hours. But beyond that, you have to study for yourself, do problems which are assigned. I will be assigning problems. I will be telling you to stop the video and derive or solve the problem or something like that. At that point of time, it is your duty to stop and do whatever is asked of you to do. Only then this course is or will be will benefit you in a proper way. So pause the video, take out your undergraduate notes, study them. Okay, now we will talk about it briefly. Okay, here are some of the concepts that you have studied. First of all, concentration means number of molecules. Say concentration of A is number of molecules per unit volume. Okay, and rate of reaction of A is the number of molecules or moles, if you like, undergoing chemical transformation per unit volume per unit time. So what we are going to say is rate of reaction is number of moles, say gram moles, reacted per unit time per unit volume. A meter cube it could be, or it could be liters. Okay. Or if you like SI units, it could be kilomoles per unit time, second, per unit volume, meter cube. Right? So that's our rate of reaction. That's what we mean by rate. It is number of moles, if you like, undergoing transformation per unit volume per unit time. That's how we are going to define rate in our whole in the whole course that we are going to do. Now this rate is dependent on concentration. It is going to be dependent on temperature, whatever catalyst you are using, maybe equilibrium. If the reaction is at equilibrium, it is decided by equilibrium constant. In general, we are going to say rate is K, concentration of A raised to M, concentration of B raised to N. So these M and N, These are called as orders of the reaction, and K is our rate constant, right? M is order with respect to A, N is order with respect to B, and K is our rate constant. So if it's a first order reaction, then the rate is kCa, and K will have units of per minute or per second, and time scale for the reaction is 1 by K. Here is an important concept. One is this K that we are talking about, this K, what are the units? It has units of Ra by Ca. What are the units of Ra? It is kilomole per second per meter cube. What are the units of concentration? Kilomoles per meter cube. Right? So this will go away. Meter cube will go away. So K has units of 1 per second, or if you like, second inverse, or it could be minute inverse. Any time inverse, it could be hour inverse. Right? So different ways in which you can write this rate constant. Recall this 1 by K, this will have units of seconds or minutes or hours. It tells you time constant, that is called as a time scale for reaction. Right? Do you recall? Maybe if it's a first order reaction, then 63.2% of the reaction happens within one time scale, one time constant. Process dynamics you have studied. So that's the meaning of time scale for the reaction. How fast or how slow the reaction is happening, on what time scale this reaction is happening. So K is like the rate, how fast or slow. 1 by K is how long the reaction is happening, whether reaction is happening in 1 second, 1 minute, or 1 hour. For a second order reaction, the rate is kCa square, and K will have units of meter cube per kilomole per second. We could have series reaction, A going to B going to C. So it is series. A reacts to B, B reacts to C. Or A could have a parallel pathway. A can react to give you B, or A can react to give you C. Okay. So these are called as parallel reactions. So these are some just basic concepts. Let's go forward. Rate of reaction is strongly affected by temperature, and how strongly it is affected by temperature is based on the energy of activation. And you remember our Arrhenius expression, ln K versus 1 by T. If you plot, you will get a straight line whose slope would be minus E by R, and then E, energy of activation, is typically 15 kilocalories per gram mole, or it could be even larger. And reactions with higher E are strongly affected by temperature. Little bit about how do we measure kinetics. So one of the ways we measure kinetics is to do a differential method. By that, what we mean is, if I measure Ca as a function of time, let's say in a batch reactor, we find out the slope at different locations. So what we are saying is we find out this slope. So let's say the slope is here at this particular Ca. This is the value of slope. At this particular Ca, this is the value of slope. And slope is nothing but, if it's a batch process, slope is nothing but how many moles are changing per unit time per unit volume, right? So that's our rate. At this particular Ca, this is the slope, this is the rate. So then we plot ln rate or ln Ra versus ln Ca. So this is our ln Ra versus ln Ca, and then you get an intercept and you get a slope. So if you take this expression, take log on both sides, so ln Ra would be ln K plus n ln Ca, right? So n is the slope, that tells you the order of the reaction, and ln K is the intercept, that tells you the rate constant for the reaction. Okay, so knowing concentration versus time in a batch reactor, we would be able to get the kinetics. When I say kinetics, what we mean is to find out. So when we say kinetics, what we mean is So when we say kinetics, what we are meaning is find K, find M, find N if it is with respect to A and B, find E, energy of activation, right? These are all kinetic parameters. And sometimes these kinetic parameters would change with respect to catalyst, right? So then you have to find out these kinetic parameters for different catalysts. So this is when we have to find out K, M, N, E. That's what we mean by finding out the kinetics of reaction. Okay, let's go forward. Okay. Or we had an integral method. Now this also we studied in our undergraduate course. What we are saying is we are going to assume. That's our first step. We are going to assume. We assume it's a first order reaction. We write an expression for a first order reaction. This is our rate of reaction and this is the rate of disappearance of A. This is based on material balance. Remember, this is based on material balance for batch reactor. Right? So then if we integrate, we will find that if you plot LNCA versus time, slope would be equal to minus K. So what we will do is we will plot the measured values of CA versus time. This is what we are going to measure from our experiment, from a batch experiment, batch reactor. And after 1 hour, what is the concentration? After 2 hours, what is the concentration? After 3 hours, what is the concentration? And so on and so forth. We are going to plot LNCA versus time. If we get a straight line, then our first order assumption is correct. If we don't get a straight line, suppose LNCA versus time is something like this. Obviously, it is not fitting a straight line. Then we have to assume a second order reaction, right? So what we might do is we will say minus dCA by dt is KCA square. So dCA by CA square is minus K dt. So if you integrate this, CA raised to minus 2 is to be integrated. So this is minus 1 by CA is equal to KT plus, sorry, minus sign is there, plus some constant of integration. Then at time t equal to 0, our CA is, let's say, CA initial, right? And then if you plot 1 by CA versus t, then you should get a straight line behavior. That's what this is telling. If you don't get a straight line, that means it is also not a second order reaction, right? If you don't get a straight line, in this case LNCA versus time, it is not a first order reaction. If you don't get a straight line between 1 by CA versus 1 by T, it is not a second order reaction. Then you try third order, then we try fourth order, right? And so on. So that is what our integral method is. So recall these two methods of doing analysis, differential and integral. Okay, next thing is different basic types of reactor. Now when we say basic types of reactor, these are the basic types of reactors that you have studied in your undergraduate course. But now in our postgraduate course, this is only some combination of these things. For example, in the undergraduate course, when you had said batch reactor, what you actually meant is that it is a batch because nothing is getting added and removed with respect to time. It is unsteady state because concentration changes with respect to time, and it is well mixed because everywhere within the reactor concentration is the same, right? So this combination In your undergraduate course, you called it as a batch reactor. This combination, that unsteady part, unsteady state and well mixed was assumed. You didn't have to think, it was there already in your back of your mind, but we have to explicitly say now because we are going to deal with so many different kinds of reactors. Second thing that you have studied is CSTR, right? You said CSTR in your undergraduate course, but what you actually meant is that it is a continuous reactor. It is operating at steady state and it is well mixed. This combination is what you called in your undergraduate course as CSTR. Whereas what we should be calling now is a continuous, well mixed, steady state. Right? Do you understand the difference now between what we have done in our undergraduate course and what is required now? Let's go forward. The third kind of reactor that you have studied is called as plug flow reactor. You said plug flow in your undergraduate course, whereas what you actually meant in your undergraduate course is that it is a continuous reactor. It is operating at steady state and the mixing behavior is like plug flow. These three you called as PFR, right? When you said PFR, you have said only this class characteristic. You automatically understood that it is steady state and it is continuous. Do you realize that? When you said CSTR, you only meant, you understood that it is, you're describing one characteristic, well mixed, but you automatically meant steady state and you automatically meant continuous reactor. Whereas when you said batch reactor, you're only saying about the flow behavior. You automatically at the back of your mind understood that it is unsteady state and it is well mixed. Do you realize the difference between what you did in your undergraduate course and what it means now? Pause the video if you want, go back and forth in this part of the lecture. This is very important part of the course, right? Understand this very thoroughly. Okay, once you have understood, then go forward. Okay, what I want you to do is, for each of these, write down how concentration of, say, reactant or a product changes with respect to time, how concentration changes with respect to space. For CSTR, as you are aware of it, how concentration changes with time, how concentration changes with space. For a PFR, as you are aware of it, how concentration changes with time, concentration changes with space. Pause the video, do this for yourself. Here is what you might have done. If you say batch, what it means is that everywhere concentration is the same. So in terms of concentration with respect to space, concentration is the same everywhere in the space. You just get a horizontal line. Whereas concentration changes with time. Of a reactant, it reduces with time. Of a product, it increases with time. Right? So that's what you might have drawn. When you say CSTR, what you meant is it operates with steady state. Right? That means concentration with respect to time is constant. whereas it is well mixed, concentration with respect to space also is constant. When you say plug flow, at any point of time concentration is not changing. At any point in the reactor, concentration is not changing with respect to time, because it is operating at steady state. But as you go along the reactor, concentration is changing, right? So you might have drawn something like this. You see, batch, whatever happens with respect to time, same thing happens with respect to space in a plug flow reactor. Whatever happens with respect to time in a plug flow reactor, the same thing is happening with respect to space here. That's why these are sometimes analogous to each other. Okay. Okay, so here is what I want you to do. So recollect from your undergraduate chemical reaction engineering course. Pause the video, do this for yourself. Relate conversion to time for a first order reaction in a batch reactor. Right. Pause and solve. Here is what you would have got. This dCA by dt. Now remember, if it's a first order reaction, this is our rate of reaction. This is RA. Whereas this minus dCA by dt, where has it come from? It is coming from material balance. So if you take a batch reactor, concentration at any time is T, concentration is Ca at any time T. After some time Ca, it is changed to Ca at T plus delta T. Correct? So if you want to write a balance, Ca at time T minus Ca at time T plus delta T, this multiplied by volume is how many moles have reacted. How have they reacted? They have reacted based on K, Ca into V. This tells you the rate of reaction per unit volume. So I have multiplied by volume per unit time. So within the amount of time delta T, these many moles have reacted. Now if you divide by delta T and take limit as delta T tending to 0 and this V you can cancel, you will get minus dCA by dt is kCA. This minus dCA by dt is coming from material balance. Material balance rate is kCA. Okay? And the rest is all mathematics. Do same for plug flow reactor. Pause the video, do it for yourself. Here is what you might have done. Again, so for a plug flow reactor, what we are saying is something comes in to this differential element, something goes out from this differential element. Now if I write material balance for this differential element, flow rate multiplied by concentration at, say, so let's say this is our V and this is V plus delta V or dV if you like, delta V if you like. Flow into concentration at V minus flow rate into concentration at V plus delta V. So flow rate is meter cube per second, let's say. Ca is kilomoles per meter cube, right? So flow rate multiplied by concentration is nothing but how many kilomoles per second enter, rate at which they enter per unit time. It is kilomoles per second. So F into Ca, so kilomoles per second and in minus kilomoles per second out. Material balance, left hand side is material balance. What is happening? What is coming in? Some of it is reacting. How much it is reacting? It is K Ca multiplied by delta V, right? That is the rate at which they react per unit volume multiplied by volume. That's the rate of total moles reacting with respect to the total moles reacting in or the total rate at which moles are disappearing because of reaction. Now if you divide throughout by delta V, what we will get is minus d by dV F into Ca is K Ca and yeah, delta V we have already done. Okay, and then if you want, you can write this slightly differently, minus dCA, and you can write it as dV by F as kCA, and then that's how you get this expression. The important point that I am trying to say is the left hand side is coming from material balance. It's about how many moles are disappearing, whereas right hand side is our rate of reaction. So first order reaction, it is kCA, right? Recall this as well as our batch reactor. Left hand side is material balance, right hand side is rate of reaction. Do this for well mixed reactor also. Pause the video, do it for yourself. Here is what you would have done. Again, if I am writing a balance, material balance across this reactor, what comes in is flow rate multiplied by concentration at the entry, inlet, in minus out, flow rate into concentration at the outlet. In minus out is what must have reacted. What is reacted? It is kCA out. Now it is well mixed. Well mixed, concentration everywhere inside the reactor is the same. So this is the rate of reaction per unit volume multiplied by V will tell you how many kilomoles are reacting per unit time, or rate of at which A is disappearing, right? And then if you rearrange, you will get flow rate. I can take out common, CAI minus CAO is kCA naught into V, and then this F I can bring on the other side, and this we write as tau, and this is what you are going to get from here. Okay. Left hand side is material balance, what comes in minus what goes out. Right hand side is the rate of reaction. This is very, very important. Very, very important. Very, very important. Whether you do in a well mixed reactor. So now you see, I am not writing design equation for CSTR. I'm not writing design equation for CSTR. What I am writing is design equation for a well mixed. I should have also written continuous steady state reactor. Right? I just didn't have enough room to write, so I've just written it as just well mixed. Left hand side is material balance, right hand side is the rate of reaction. That's important. Okay. And you might have studied this as well, very famous plot from Levenspiel for a given reaction, let's say first order reaction, how the residence time required for CSTR compares with that of PFR. And you already know that for a given first order reaction, if you have let's say 99% conversion, so this is 1, that means 100 minus percent, so 99% conversion is here. If I use 1 CSTR, the volume of CSTR required would be double that of a plug flow reactor, right? Sorry, it is here. Here, this is for one reactor, second, third, fourth. So it is here. It is something like 20 times that of a plug flow reactor. Okay, you've done all these things. What I would like you to do now is to look at some of the problems. I'm going to give you some problems. Solutions are not there. You find out solutions for yourself. These are based on Levenspiel. So do these problems for yourselves. Stop the video. Do this problem for yourself. So in a batch reactor, concentration of the reactant at the end of at the start of a reaction is 1 gram mole per liter. After 8 minutes, 80% conversion is obtained. After 80 minutes, 90% conversion is observed. Find rate expression. Right? Let's assume that it is isothermal right now, like your undergraduate. So these examples are essentially from your undergraduate course. Pause the video, do them for yourself, do them yourselves. Discuss with your classmates if you want. Second problem, in a batch reactor containing 10 meter cube of pure aniline, shows the following concentration of aniline with respect to time. After 1 hour, concentration is 10 kilomoles per meter cube. After 2 hours, it is 7.98, 4 hours, 3.29, 6 hours, 2.04, 8 hours, so on and so forth, right? If you want, you can make this as 0 time if you like, right? So make this change if you want. Let's just change this little bit, right? Let's just change. Right, let's just change. So we have changed that. So our 0 time means our initial concentration, right? So this is like a concentration versus time. Just to give you some hints, concentration versus time is like this: 0 time after 2 hours, 4 hours, 6 hours, 8 hours, 10 hours, 12 hours, right? You can find, you can do this by differential method, you can do this by integral method, choice is yours, right? Once you do that, I would like you to find out how much residence time is required in plug flow reactor to achieve 99.5% conversion. How much residence time is required in CSTR to achieve 99.5% conversion. It's something to do with this kind of a plot. Right. Okay. Here's the next problem. Gas phase reaction to A goes to B is carried out in a constant volume batch reactor. Constant volume batch reactor. Reactor is evacuated completely filled with pure A at 1 atmosphere, 25 degrees centigrade. Reactor is heated quickly, 100 degrees centigrade, and pressure change is noted with respect to time. Right? Notice the 0 time data is not given. So what we are saying, 25 degrees centigrade concentration or partial pressure of A is 1 atmosphere. Up to 100 degrees centigrade, what would be partial pressure? This would be 1 atmosphere multiplied by 373 divided by 298. If you like, you can make it 373.15 divided by 298.15. This would be at time equal to 0. This would be partial pressure of A at time equal to 0. Right? And since we are starting with pure A, this is the same as total pressure. But now, beyond now the reaction starts. Now the reaction starts. So after 1 minute, our total pressure is say 1.14 atmosphere. But this, within 1 minute, some reaction must have happened. So partial pressure of A must be there and partial pressure of B must be there, because some B has formed. How much it has formed? Based on this stoichiometry. So use this stoichiometry to calculate partial pressure of A and partial pressure of B with respect to time. Right? Complete this table at 1 minute, 2 minute, 4 minute, 6 minute, 8 minute, 10 minute, 15 minutes, and so on. Now you have partial pressure with respect to time. You can convert that to concentration if you want. How is partial pressure and concentration related? Concentration is partial pressure divided by RT. What we are assuming ideal gas law. Okay. So then you will have concentration of A versus time. Then you can find kinetics. Okay. Rate expression. Next problem. Reaction A going to B shows a rate constant 3 liter per gram mole per hour. Inlet to the reactor has a flow rate of 10 liter per hour and inlet concentration of 0.5 gram mole per liter. Calculate the volume of a well mixed reactor and PFR required to get 99% conversion of it. Right? You have done these kinds of problems in your undergraduate course enough number of times. I'm just giving you as an exercise to refresh your memory. So first of all, pause the video, do it for yourself. Okay, so what does this K tell you? It's a second order reaction. So our rate must be K Cs square rate. Where did that rate go? Right. Now We want a well mixed reactor. Well mixed means continuous steady state well mixed. So flow rate Ca in, Ca out, and a plug flow reactor. Flow rate Ca in, Ca out. We want 99% conversion of A. So what can we say about Ca out by Ca in? 99% is reacted, only 1% is remaining. So Ca out must be 0.01 times Ca in. What do we know about flow rate? Flow rate is 0.5 gram mole, flow rate is 10 liter, flow rate is 10 liter per hour. What do we know about inlet concentration? 0.5 gram mole per liter. Right? Find the volume. Which one would require lesser volume? Well mixed reactor or plug flow reactor? You already know from your undergraduate course. Plug flow is going to require less volume. Well mixed reactor is going to require more volume. Do this for yourself. Certain gas phase reaction shows the rate expression. Ra is 2.3 Pa square at 400 Kelvin as well as 500 Kelvin. Ra is in units of gram mole per meter cube per second and Pa is in units of atmosphere. Find the energy of activation. You might be tempted to say pause the video, do it for yourself. You might be tempted to say that rate does not change with respect to temperature. Energy of activation is 0. Aha, be careful. Okay, do this for yourself. Concentration versus rate data for a reaction is given below. Find the time required for concentration to reduce from 1.3 to 0.3 in a plug flow and well mixed reactor. Okay. So what we typically do is we plot Ra with respect to Ca. Right? How would it look like? Some way it will look like, right? Maybe like this. We don't know. Just don't worry about it. Well mixed. What do we mean? At the exit concentration. What do we have to do? At the exit concentration, this is the Ra. Let's say at Ra at Ca equal to let's say 0.3. So 0.3 is here. Ra is this value. And for a well mixed reactor means Ra is constant, same throughout, whether it is inlet or outlet, whether at the entry or exit, Ra is the same. Right? So these kinds of things you have already done. Right? Where you have to do integration, area under the curve, or where you have to do draw a rectangle and things like that, right? So recall all that. So what we are going to do in this course is, this is what we have done so far. We have just done some basic revision of basic concepts. Next thing that we are going to look at is real life reactor. What are the design aspects, multiple steady states, and reactor stability? These are the three things that we are going to do first. What are the real life considerations when we start designing a plug flow reactor? What are the real life considerations when we start designing a well mixed reactor? What are the real life conditions when we start designing a batch reactor? And then which one should we take? Whether you should take batch, whether you should take well mixed, whether you should take plug flow. Then we'll do a little bit about non-ideal flow in reactor. So remember what I told you initially. Look at this characterization. Initially, for the first few lectures, what we are going to do is to look at basic well mixed reactor, batch reactor, plug flow reactor. Right? This is what we are going to do. We are going to look at under adiabatic operation, Non-adiabatic means either isothermal or diabatic operation. We are going to look at them operating at steady state, operating at unsteady state. We are going to look at whether it's a batch process, whether it's a continuous process. So these 4 things we are going to look at in some initial lectures. So under this category of real life reactors, and then we are going to look at non-ideal flow in a lot more detail. Right? So that's point 2 and point 3 in our course. Subtopic 2, subtopic 3. Subtopic 4 onwards, we are going to look at multi-phase reactors. Look at this. Subtopic 2, subtopic 3. Subtopic 4, 5, 6, we are going to look at solid catalyzed reaction. Multi-phase reaction between a fluid reaction in the fluid catalyzed by solid particle, or reaction part 5, a little bit more about how these reactions, how the reactors are designed for fluid solid reactions. It could be a reaction between liquid in a liquid catalyzed by solid particles, or it could be a gas phase reaction catalyzed by solid. In general, we are going to say fluid solid catalytic reactions. And in the last part of the course, we are going to look at fluid reactions. Okay, so this is based on the last 4 concepts of our classification. These 3 are based on our first classification, heterogeneous. And in each of these, even when we start doing heterogeneous reactions, say gas solid or fluid solid or fluid reactions, we'll have to worry about whether it's a batch or a continuous, whether it is steady or unsteady, whether it is plug flow or well mixed, whether it is adiabatic or isothermal. Right? These are the characteristics. Again, I am emphasizing these characteristics. These are the only characteristics you need to describe to design any reactor in the world for any process. Okay, that's how easy reaction engineering is. Just describe these 5 things mathematically, and your reactor design is done. That's so easy, that CRE is so straightforward. Again, I am emphasizing these are the few things that you need. These are the things that you need. Homework for you. Levenspiegel's book, everybody must be aware of, 3rd edition. If you see chapters 2 to 5, that's what these 5, 6 problems that are there, they are based on these chapters 2 to 5. If you want to solve more problems, you can solve 2.13. Sorry, not if you want to. So you have to solve these additional problems as well. 2.13, 3.19, 3.28, 5.5, 5.11, 5.25, 5.30. I have just prescribed 7 problems. Okay. More number of problems that you do, better it is for you. You will be better prepared for the next class. Important thing is whatever homework is assigned, do that before the next class. Okay? Only then you will be prepared to understand what is being talked about in the next class, and revise undergraduate concepts. Our whole course is based on that. It is at an advanced level. Okay? Basic concepts are the same. They are going to remain the same. Okay? Solve these 7 additional problems, then you will be in a better position to go forward and see the second lecture and so on. Okay, so we'll stop here, this lecture here, and we will start with our course. This was just the background. We'll start with our course now, different parts of our course from the next lecture onwards. Okay, revise, solve problems, do homework. See you in the next class.